Let me chapter 5. We start a new chapter now on operations on kernels. Operations. On kernels. We have seen marginally some occasions of this, in particular when we add two kernels together. Now we want to do it more systematically and see when can we multiply or take the difference of two kernels and what is the space we obtain. That's the purpose of this. The first section is something standard that we do usually in structures which are real, but we want to create something which is complex. So if you have H, which is an RKHS on X, but real valued, it's simply, I mean, this is the most natural way to do it. Consider H plus IH, which means all the functions F plus IG, when F is in F and G, both are in H. This is called complexification. And it's easy to see that W is a vector space, but we need to also define the inner product. And the inner product, what is inner product of F1 plus I F2 and G1 plus I G2 in W. And simply we ask ourselves what we want this to be. We want to be an inner product, so we should be able to expand. And when we expand, it will be F1 inner product G1 in W plus F1 inner product of IG2 in W. What we take out, this becomes minus I. And then plus IF2 inner product with G1 in W, and I comes out, becomes plus I. And finally, IF2 inner product with IG2 in W, I and I from both components come out. It's I times minus I gives us minus. So if we want to have an inner product, it has to satisfy this property, this identity. So, and now F1, G1, F2, G2, I mean, all of this inner product, even though they are in W, but they should be compatible with the one on H. So we want this to be F1, G1.
Excuse me, I think the last minus sign should be a plus.
Yes, yes, thank you. This I times minus I, absolutely, thank you. Yes. And now we want this to coincide with what we have before. So inner product of F1 and G1 is this, in W is this, we want this to be the same as the one in H. And the same, I mean, a little bit of space here. This we want to be minus I F1 G2 in H plus I F2 G1 in H, and the same with plus F2 and G2 in H. We want this to be true. And now we consider this as our definition. We define this to be equal to this as our definition. definition. And then the rest is just a matter of calculation to show that this is a good definition. It means that it satisfies all the properties that we want to behold, and they are held. And in particular, we see that the norm, so the rest is just some verification. I leave it to the student to do it. And in particular, you see that the norm of this element in W squared, based on the definition, is the norm, the first one in H squared plus the norm of the second one in H squared. This is what we want to be true indeed. And also, again, about the kernel, what is the F1 plus I F2 inner product with ky, the kernel that we have for H. So this is a real function in W. Based on the above definition, is F1 K1 in H plus I F2 and Ky in H. That's our definition. And based on the property of the kernel function, the first one is F1 evaluated at Y plus I F2 evaluated at Y. So in other words, if I call this function F for any F in W, F inner product with Ky is F at point Y. The kernel doesn't change. Is the same. We have the same K as before. It's just the space which is complexified. So this is something very standard that we do in other contexts too. That's in the context of RTHS. The next topic, which is about differences and sums, plus and minuses. There is a result which is used in the proof of the next theorem, which merits to be highlighted by itself. And in a sense, even though the proof is easy, it is used many, many times, even in research articles. And it's a powerful tool just for RKHS and its generalization, which is RKBS, reproducing kernel, in a sense, Banach spaces. So as I mentioned it as a lemma. Suppose that H and K are given, reproducing kernel Hilbert spaces. Both are given. And you have a mapping T, which is defined from H to K. Of course, linear, everything is linear. So just a mapping is well defined. It means that if F in H is given, then T of F belongs to K. So it seems nothing extraordinary up to here. What is amazing is that then T is automatically bounded. If you have a mapping, linear mapping, which is just well defined, then boundedness is a gift. It comes automatically. And the proof is based on the closed graph theorem. Slide. Here. It's a powerful tool from function analysis. It says that if you have a sequence in H and F is also in H and G is in K and Fn, these are our assumptions. Fn goes to F in H and Tfn goes to G in K. So from this hypothesis, you can show that Tf is equal to G. Then the whole thing, if we can show this, which means the graph is closed. That's precisely the same thing, but written in mathematical language and more explicitly. Then this implies that T is bounded. That's the theorem, closed graph theorem. If the graph is closed, then the mapping is bounded. And now, how can we verify this? That's the power of RKHS. Well, Fn Fn goes to F implies that Fn of X goes, there is something missing here. Please let me, I mentioned this, but I'd gone back and complete it later on. There is one there's one hypothesis which is missing here. I'm sorry for that. For any X in X, and the same is for K. I mean, Tfn of X goes to G of X. No, sorry. I tell you why I wasn't careful enough here when there is something here to conclude that Tf at all point X equal to G of X for every X. And so Tf is equal to G. This I forgot, and you'll see in the application why I forgot. Because our mapping is the inclusion mapping. And so when it's inclusion, you can easily remove this T and Cfn also goes to G and conclude. But there is a generalization. And I mean, I should come back and give you a more precise formulation. I'm sorry for that. So back in, not next week, next time. I will complete this. But still, this theorem this lemma is a very powerful lemma. Just one hypothesis is missing. If just it's well defined, you can go further and show that your mapping is bounded. And I forgot this because my mapping is just inclusion, and I can easily go to the end. Again, my apologies for that. So our first theorem is for the inclusion, which gives us the difference later on. Here is the theorem. X is a set, K, K1 and K2, both of them, are from X times X with values in C. These are kernels. And then here is the conclusion. Then H of K1 is a subset of H of K2 if and only if and only if there exists a constant C such that the relation between kernels K1 is less than or equal to C2 K2. So up to here, it's just an inclusion of two spaces is equivalent to a condition on the kernels. And I mentioned before the break, K1 less than or equal to a constant K2 is a huge restriction. You have to verify it on all n by n matrices with n equal to 1, 2, 3, no restriction on n, and no restriction on other nodes x1 up to xn. So we have many matrices to verify that this matrix is less than or equal to C times that matrix, infinitely many. Well, this is for the first part, but we can say a little bit more about C. Moreover, the norm of F in a space H2 or HK2, we can simply write 2 here, which means in the second space, is less than or equal to the same constant C, norm of F in H1 in the first space for all F in H1 or HK1. So the inclusion map is bounded by C. The best constant is indeed the norm of the inclusion map. That will be shown in the proof. I give you the complete proof, and you will see what went wrong when I wanted to prove the previous lemma. Now, first assume that the constant C exists. Assume what happened. Assume that C bigger than or equal to exists. And well, K1 is less than or equal to constant times K2. Now, if F is in H of K1, and we can normalize it, it really doesn't matter. I will tell you what happens if we do not normalize it. Then, by the famous theorem that I used even today a couple of times, I can say that f of x, f of y bar is less than or equal to 1 here, which is the norm of f1, times k1 x and y. You see here the effect of 1 is here. Otherwise, here you have norm of f1, norm 1 of f squared. So this is from the previous, famous result that I mentioned several times by the theorem. I think it was either 3.1 or 3.11. I forgot the exact numbering, but the theorem we use several times. And our assumption is that K1 is also majorized by K2. So put this together, we see that f of x, f of y bar is less than or equal to C2, K2, x and y. And one more time, the same theorem says that f is in h of K2, and also its norm is majorized in this space, is majorized by C. For a general f, if f is in h of K1, you can consider f divided by normal f in the space. Now it is normalized, and you obtain the same conclusion. F is in the second space, and also its norm in the second space is controlled by C. In other words, normal F. In the second space, you multiply both sides by this. Is controlled by C times normal in H1. That's half of the theorem, but even in this half, I used the theorem to 3.1 or 3.11 maybe twice, and even before the break, I used it several times. And now for the converse. For the converse, just assume that h of K1 is a subset of h of K2. And consider the mapping for which in the lemma I faced some problem. The mapping from h of K1 to h of K2, just the inclusion map. It's well defined because h of K1 is a subset of h of K2. And now for this, it's trivial to apply the closed graph theorem if you have Fn in the domain which goes to F in h of K1, and in the range T of F, which is F, goes to G in h of K2. Now we can use the fact that convergence in norm implies convergence pointwise. So this implies that Fn of x goes to f of x for every x. And this one implies that Tfn of x, which is Fn of x, goes to g of x for every x. And therefore, for every x, f of x is equal to g of x. So f is equal to g. In other words, g is equal to T of f. And so closed graph theorem implies that, say, by closed graph theorem, T is bounded. T is bounded, and so I can write norm of TF is less than or equal to a constant T norm of F. But note that this is in 2 and this is in 1. But T of F is equal to F. So normal f in 2 is less than or equal to a constant normal f in 1 for any f in H1. For any f is in H1 or f of k. It's not over yet. What I did is that from just h of k1, what was my assumption? That's not the mistake. My assumption in the second part was that h of k1 is a subset of h of k2. And from this assumption, I concluded that a normal f in H2 is less than this constant normal f in H1. So this is what I have shown up to now. But my goal is more than that. My goal is also to show that the kernels are K1 is controlled by the kernel K2. And for this, there is a trick. And it's a nice trick, but it's not a trivial one. Here is the way we do it. So remember our goal. So our goal is to show that K1 is less than or equal to a constant K2. So how we can do that? Again, we need to consider what is the meaning of this. And for this, we consider endpoint in X and alpha 1 to alpha n is in C. And for simplicity, we write ky1 for the reproducing kernel of the first space, k1, if I evaluate at x and y, and ky2 for the second space. So these are our kernels. Now, what can I say about this combination? Sum alpha I bar, alpha j, k1 xi, xj. Well, of course, I can write it ij from 1 up to n, alpha I bar, alpha j. This is the same thing as little k at point xg, but in the first space k1 evaluated at point xi. And usually, and this is true, I write something here, but I will erase it. We write this as k xj1 evaluated at the point xi, so it will be k xi at the point 1 in the first space h1 or hk1. This is perfectly fine. This is true, but at the same time, use the fact that our main hypothesis that hk1 hk1 is in hk2. So this element, it is true that which is in hk1, it's also is in hk2. So I consider it as an element of the second space, a function evaluated at point xi. So I can write K2 at point xi in the second space. That's the trick. This is something that if you don't do it, it doesn't give you the result you are looking for. So the main point is here. Switching from space 1 to space 2. And then the rest is mechanical work. You take the sum inside, j from 1 up to n. Oh, not twice. Alpha j k xj1 sigma I from 1 up to n alpha I k xi in space 2 h k2. And I mean, if you wish, you can take the absolute value, but it's not needed because we know this combination is already positive. So apply Cauchy-Schwarz. So it's less than or equal to the norm of this times the norm of this, but both norms in the second space. Sum j from 1 up to n alpha j k xj1, and here I from 1 up to n alpha I k xi2. And now it's time that I need this inequality, which I already proved, this inequality. For any element of the first space, of course, we can calculate the norm in the second space, but the norm in the second space is controlled by the norm in the first space. And I use it here. This is an element of the first space, but the norm is computed in the second space. So I can write this less than or equal to, I mean, the constant that we have before was constant C, which is the norm of T. The norm of the same object, alpha j k xj1, but this time in the first space. And the second doesn't change. So this allows us to go from 2. Oh, no, this is not good. This allows us to go from 2 to 1. And now look at this. And the one that we started with, this. It's very easy to see that if you square this quantity and use the fact that this is the kernel, you obtain the same thing that we have at the beginning. In other words, we have shown that the norm of the sum j from 1 up to n alpha j k xj1, the one we have before is this one squared, is less than or equal to C, and I repeat it here. One times, and I repeat this one too. Kx1 squared. And now we can remove one of this and just obtain the sum j from 1 up to n alpha j k xj1 less than or equal to C. Alpha I kxi, I think 2 is forgotten from some point on. There is a 2 which is forgotten here, forgotten here, forgotten here. 2. Well, almost at the end. I already said that if you square this, you obtain the combination that we have here in the yellow rectangle with K1 here. So if you do this here, if you square both sides, then this one gives us the sum ij from 1 up to n, alpha I bar, alpha j, k1, x1, xi, and xj, less than or equal to C2. And this one gives us alpha I bar, alpha j, k2, xi, and xj. And this is precisely the meaning of K1 is less than or equal to a constant K2. And you see the constant C equal to the norm of T works. So that's the end of proof. The proof is nice one, but it really doesn't work if you do not apply this trick here. The heart of proof is here, that instead of considering this as an element of H1, consider it as an element of H2, and so apply the kernel of the second space. And then the rest is, I mean, somehow mechanical, and you go up to the end. A special case which is very important is the contraction when C is equal to 1. In this case, we say that H1 is contractively included in H2. So if H1 is a subset of H2, but more than that, norm of H in 2 is less than or equal to norm of H in 1 for any element of the smaller space. In this case, we say H1 is contractively contained in H2. And the previous theorem gives a complete characterization of this. So corollary, as before, H1 and H2 are KHS on a space X, and with kernels with kernels respectively K1 and K2. Then H1, very nice characterization, is contractively contain H2 if and only if this is difference K2 minus K1 is positive. It's the same as K1 is less than or equal to K2, but it's more practical to write it that way. And we didn't go into this example in detail, but we just mention it as an example. But we had a week on this topic on Dobranche Wozniak spaces. For these spaces, we consider B as an element of H infinity, but norm is less than or equal to 1. So in the unit ball, in the closed unit ball of H infinity, and the kernel of this space, I mean, it's called the space HB. The kernel is 1 minus BZ BW bar 1 minus ZW bar. Indeed, there are 3 different ways to define HB spaces. And there is a nice article of Joseph Ball on this. One method is to consider with this kernel, show that K, I mean, so we start with this definition. It's a little bit of work, but we show that K is bigger than or equal to 0. And therefore, by Moore theorem, it gives a space, H of K. And this is precisely our space HB. That's one way to define it. So starting from kernel, we get this space. If we do it that way, well, you need a little bit of work to distinguish some of its elements and develop some of the properties of HB. Another way, which I mean, we adopted in our book, and Saracen has a very, very nice book on sub-Hardy Hilbert spaces, and indeed, this is, I mean, his way. He invented this this approach. We use tuplets operator to define HB as a function space, and then we show that is an RKHS, and its kernel is given by this one. This second approach is better, and you easily prove, more easily prove some of the properties of HB spaces. The reason I mentioned this here, the reason is that, I mean, I just mentioned as a result that HB is contractibly contained in the Hardy space H2. It's one of the famous examples of contractive inclusion. So they are there, and so any F, well, we can put it this way, nor what does this mean? Is that HB is in a subset of H2, but more than that. Norm of F in HB is less than or equal to the norm of F in H2 for any F in the smaller space. That's the meaning of contractive inclusion. I mean, don't go into the detail of this. It's beyond the scope of our course, but if you're interested, I mean, as I said, there is book of Saracen, and there was a week on this topic, courses given by Dan Timotin. You can go there and I mean, watch his lectures, and these are all explained over there. That finishes the part about inclusion and differences. We can continue and talk about sum. Now, what do we obtain if we add two kernels? I think I have enough time to explain a little bit, but the proof we will see. Here is a theorem. Same hypothesis as before, H1 and H2 are KHS on X with kernels K1 and K2, and define or put K is equal to K1 plus K2. Well, if you add two positive kernel function and the result is positive, there is no extra condition here. But still, there is a question. What is H of K? Then H of K is what you imagine it has to be, is the set of all F1 plus F2 such that F1 is in H1 and F2 is in H2. But be careful here. The representation is not unique. I mean, different elements, different F1 and different F2, you may add them together but obtain the same object. So if, moreover, for any F in HK, it is true that F can be written as F1 plus F2, but what can we say about the norm of F squared? This is equal to the minimum of all possible representation of all F is equal to F1 plus F2, F1 is in H1, F2 is in H2. And the norm is the norm of the first one in the first space squared plus the norm of the second one in the second space. Either put 1 here or H1 or H2 squared. So you cannot say that the norm of F squared is equal to the norm of F1 squared plus norm of F2 squared because of, I mean, non-uniqueness of the representation. But you can take the infimum, and instead of infimum, I wrote minimum. It's attained. And now let's go to proof. Consider the direct sum of H1 and H2. This is the ordered pairs F1 and F2. With the, I mean, usual way to define the inner product on this space means that the pair F1, F2, its inner product with G1, G2. It's component by component. This one with this one, but they are in a space H1, and F2 inner product with G2, they are in H2. And this gives the inner product in the direct sum. So it's easy to, the rest is easy to prove that this is well defined and we obtain a Hilbert space. And the norm, moreover, that in this space, in H1 plus H2, the norm of pair F1, F2 squared is equal to the norm of the first component squared plus the norm of second component squared. Good. And now consider this null space. I mean, we will see why it's n, why it's null space. The set of all ordered pairs of the form f minus f, when f is in intersection of h1 and h2. This is minus. So we consider this. It's easy to see that it is a vector space. I mean, closed under addition and scalar multiplication. It's also norm closed, because if fn and minus fn is in n, and converges to the pair f and g, then by the definition of convergence, then the first fn should go to f in h1, and the second component, which is minus fn, should go to g in h2. True. That's the meaning of this convergence. And therefore, this implies that f is equal to minus g, but f was in h1, g was in h2. So for this is in h1 intersection h2. And therefore, the pair f and g is the same as the pair f minus f stays in it. So it's a closed subspace of H and is a closed subspace of H1 plus H2. Therefore, I can write H1 plus H2. I can decompose it as n plus, this is orthogonal decomposition, n perp. So any element f1 and f2, which I consider, I can write it uniquely as an element of the null n, which means f minus f, plus another element h1 and h2. This is in n perp, and this is in n. This is possible. So why is this helping us here? Because I can consider the mapping gamma. Now you see why is it called n. The mapping gamma from h1 plus h2 to a vector space, which is called, I call it H. For the time being, there is no structure on it. It's just the sum of element of H1 and H2. Note that H1, it's element of functions on X, complex function, the same thing as this one. So when you add a function here to a function here, it's an element of the family of all functions defined on X with values on C, and we call this H. So the definition is like this: simply F1 and F2, you send it to F1 plus F2. That's the definition of H. No structure on H yet, except that it's a vector space. And the kernel, or the null space, better to say null. Null space of gamma is precisely what we called N. Because it's all f1 and f2 such that f1 plus f2 is equal to 0. When this is the case, f2 is minus f1, so we can write it as f minus f, and f is at the same time in h1 and in h2. This is the space we call n. So the null space is n, and therefore we can say that if we restrict gamma from n plus to h, we obtain a mapping which is bijective. True, because now the null is linear, and now the null space is just 0. So we obtain something which is bijective. And I explained this before in the middle of our course, that it happens sometimes that we have two sets and a bijection between them. Say, we call this set, say, X, this set Y. And there is a structure on the first space, and this map is bijective. And we can use this bijective map to transfer the structure of X to Y. So we define a structure here just by copying. In other words, you take, for example, if the structure is an inner product, what is the inner product of two elements here? Bijective, you go back to the first space by your map, and you obtain two elements here and there. You calculate the inner product of these two elements and define the inner product of these two to be the same. And for any other operation, the same. For example, if you want to define a group, the same thing, vectors, whatever is here by the bijection can be transferred to the other space. Well, we are in the middle of proof. Still, I need probably 10 more minutes to finish this, but it's 4:02. Let's have a break and come back after the break to finish the proof.
I have a quick question.
Please.
I didn't catch that remark that you made about the lemma. Was it true under certain other conditions?
Yes, I remember. I mean, after the lemma, let me share again to show you. I failed to prove the lemma because of was it on this or on the other one? I think it was in the. Here it is. I have to show this. True.
Right.
But I couldn't. And the reason is that I need more information on TFN at the point X and its relation to Fn of X. I didn't add in this lemma. I wanted to generalize, and I tell you now, I can tell you why, because I remember. In the application, I didn't need this because TFN was precisely equal to Fn. So if Fn goes to F and Fn goes to G, F has to be equal to G. The general version I needed, the T of Fn was just a multiplication. So Tf was a H times F, something like that. And now again, you see there is a connection between TF at point X and fx is h of x, f of x. And I can apply the closed graph theorem in the following sense. If fn goes to f and tfn goes to g, then here I can say that fn of x goes to f of x. What can I say about tfn of x? Tfn of x, here is the definition, is h of x, fn of x goes to h of x, f of x. On one hand. On the other hand, I assume that it goes to g. Also, it goes to g of x. And therefore, g is equal to h times f. In other words, is equal to t of f. And therefore, I can apply the closed graph theorem. In this general setting, which I mentioned here, the thing I forgot is to somehow connect TF to F.
I think the way to do that is to have the hypothesis that the map that takes F to TF evaluated at X is continuous on H for every X in the domain space of K.
So for any X in X,
F goes to TF evaluated at X. You need for that to be continuous on H. That's the missing hypothesis.
okay. And then if Fn goes to F, oh yes, then we can go. And of course it works for this
Works easily for that, and if T is the identity also.
Yeah, for inclusion it works, for multipliers it works. So yes, this is a good one. I didn't think of this. Thank you, Sheldon. I will write this correctly for the next time. So the point evaluation is continuous with respect to the structure of H.
Are there obvious examples where this would fail without either of those conditions?
Yes.
Or-
So because otherwise, even if you take H equal to K, if you don't add any hypotheses, you're claiming that every linear map is bounded.
Yes.
Okay.
This
Right?
is not true. This is not true. Yeah. Yeah.
Okay, thanks.
Thank you indeed. And thank you, Sheldon.